Let's be honest, if the words Lagrange error bound make you a little nervous for the AP Calculus BC exam, you are definitely in the right place. By the end of this, you'll see it's not just some scary formula. It's actually your secret weapon for acing those Taylor polynomial questions. So here's our game plan. First, we're going to tackle why we even need an error bound in the first place. Then we'll dive in and break down the formula itself, piece by piece. After that, we'll tackle the trickiest part, the hunt for M, walk through a full example, and then wrap it all up with some pro-level tips to make sure you nail this on exam day. Okay, so let's set the stage. Whenever you use a Taylor polynomial, you're essentially making a trade-off, right? You're swapping a really complex function for something much, much simpler to work with. But that immediately raises a huge question. And that question is, just how good is that simpler version? I mean, think about it. Without some way to know how far off you might be, your approximation is really just a shot in the dark. We need a way to actually measure our confidence in the answer we get. So how do we get that confidence? Well, this is where the Lagrange error bound comes marching in. The best way to think about it is as a mathematical guarantee. It gives you a definite, absolute upper limit on your error, turning what was a guess into a genuinely reliable number. I absolutely love this analogy. The formula really does act like a safety net. Imagine your approximation is you, walking a tightrope. The safety net doesn't tell you exactly where you'll land if you fall, but it does tell you, hey, no matter what happens, you will not fall further than this. It gives you a maximum boundary for your error.
Now, the full formula can look a little intimidating all at once, so let's not do that. Let's build it up. It all starts with this term right here, r sub n of x, inside absolute value bars. This is just a fancy way of saying the remainder. It represents the actual real-world error, the gap between the function's true value and what your polynomial estimated.
Okay, so what controls the size of that error? Two main things. We have this mysterious m on top, which is a maximum value we'll have to find in a bit, and it's all divided by n plus 1 factorial. Now, pay close attention to that. It's not n factorial, it's n plus 1 factorial. It's always based on 1 degree higher than the polynomial you used. And here it is, the final piece of the puzzle. We multiply that whole fraction by the distance between our point x and our center c, all raised to the n plus 1 power. This part is what makes it all so intuitive. It just means that the further you stray from the center of your approximation, the larger your potential error can become. It just makes sense. All right, so let's do a quick roll call of all the players here. R sub n is your error, the thing you're trying to pin down. N is just your polynomial's degree. C is the center you built it all around, and X is the spot where you're making your guess. And then there's M. M is the star of the show. It is the absolute maximum value that the next derivative, the n plus 1th one, can possibly reach on the interval we care about. Okay, let's be real for a second. Finding this m value, this is where most people get tripped up. It feels like the most challenging part of the whole process, for sure. But here's the good news. There's a clear 4-step recipe you can follow every single time. It's not guesswork, it's a system. And here is that system, your 4-step hunt for m. Step 1, find the next derivative. If you have a 3rd-degree polynomial, you find the 4th derivative. Simple. Step 2, define your interval. It's always just from your center C to your point x. Step 3, analyze that derivative's behavior on that specific interval. Is its absolute value just going up or just going down? And finally, step 4, pick the single largest absolute value it hits on that interval. And boom, that's your m. All right, that's a whole lot of theory. Let's make this concrete. The best way to really get this is to just do one. So let's walk through a classic example together, from start to finish. So here's our problem. We're going to use a 3rd-degree Taylor polynomial for the function e to the x, and we're centering it at x equals 0. The big question is, what's the maximum possible error we could have when we use it to approximate the value at x equals 0.5?
Okay, time to hunt for m. Our n is 3, so we need the n plus 1th or 4th derivative. Now, we got lucky with e to the x because every single derivative is just e to the x. Super nice. Next, our interval. It goes from our center, 0, to our point, 0.5. So we're looking at the interval from 0 to 0.5. Now, what does the function e to the x do on that tiny interval? Well, it's just always increasing, right? That means its maximum value has to be at the right endpoint. So m is e to the 0.5 power. That's about 1.649. And you know what? To make our lives easier and to be extra safe, we can just round that up to a nice, clean m equals 2.
And now for the satisfying part, we just plug everything into the formula. Our m is 2, our n plus 1 is 4 factorial, and our distance x minus c is just 0.5. Run those numbers and you find that our error has to be less than or equal to about 0.0052. This is the whole point. We now have a guaranteed boundary. Our approximation is officially trustworthy. So, you see how the mechanics work. Now, let's pivot and focus on what you're really here for, how to use this knowledge to absolutely crush these questions on the AP exam. You have got to watch out for these 3 common traps. Seriously. First, using the wrong derivative. I'm going to say it again. It is always n plus 1, not n. Second, analyzing the wrong interval. It's just from c to x. Don't overthink it. And third, underestimating m. Remember, this is an upper bound, so being a little too high with m is safe. Being too low is wrong. Now, this is a huge strategic point for the exam. You have 2 main tools for error, and you need to know when to use each. Lagrange, our heavy-duty tool, works for any Taylor series, but you have to do that hunt for m. Then there's the alternating series error bound. It's way easier. The error is just the absolute value of the first term you didn't use. But, and this is a big but, it only works if the series alternates signs, the terms get smaller, and they head to 0. If those conditions aren't met, you must use Lagrange. So here it is, your final checklist for success. 1. Get lightning fast and accurate with your derivatives. 2. Memorize that Lagrange formula cold. There's just no way around it. 3. Really understand what the pieces mean so you're not just mindlessly plugging in numbers. 4. Practice those tricky problems where they give you the error and ask you to work backwards. And 5. Please double-check your arithmetic. A simple mistake with a factorial can cost you everything. And look, I know this can feel like just another abstract topic for a test, but it is so much bigger than that. When engineers at NASA are plotting a trajectory for a spacecraft, or when analysts on Wall Street are modeling financial risk, they are using approximations. And the only reason they can trust those models is because of error bounds just like this one. This is what turns a good guess into reliable, real-world science. So let's end with this thought. The Lagrange error bound isn't just about finding a number. It's about finding certainty. It takes an approximation, something that is inherently a guess, and it puts a hard, reliable boundary around it. It gives you confidence. So the real question is, now that you have this power to measure error, what can you go build with that confidence?